Hello everyone, my name is Luan Teylo. I'm a former PhD student from the Federal Fluminense University, and today I will present the work Compare SARS-CoV-2 sequence using a commercial cloud with a spot instance-based dynamic scheduler. So, let's start. Biological sequence comparison is one of the most important operations in bioinformatics. It is used as a building block for applications that deal with evolutionary studies, drug designs, among other kinds of applications. And the goal of pairwise sequence comparison is to obtain a score and an alignment that represent the similarity between the sequence. So for example, here in this figure, we have two sequences with 10 base pairs each. As we can see, a match value is assigned, as for example here, when we have the same character. A mismatch value is assigned when we don't have the same character, as for example here. And finally, a gap value is assigned if a space was introduced in one of the sequence. So after the assignment of the values, we have the score and the alignment. So as we know, the COVID-19 pandemic study is of particular interest nowadays, and the comparison of SARS-CoV-2 sequence is crucial to understand the disease and predicting how the virus will evolve in the future. So since several SARS-CoV-2 sequences are being published daily, genomic studies should be done regularly to track new mutations of the virus. And in this work, we want to show that cloud computing can play a fundamental role in this kind of operation. First, because the cloud is a very powerful multi-core platform, and also because the cloud allows that biologists or scientists concentrate on the results instead of concentrate on the computational infrastructure. In the last years, we see a undergoing adoption of the cloud computing environments for different kinds of applications, and that happens because cloud has some technical and economical advantages when we compare with other platforms like grids and clusters. For example, in the cloud we have immediate access to computational resource without upfront capital investment, and in a pay-per-use model where we pay for what we actually use it. The most common way to contract computational resource in the cloud is through the acquisition of virtual machines. So if we want to contract a machine on the cloud, we can choose among different types of virtual machines with different computational resources such as the number of vCPUs, memory capacity, network, and even the usage purpose. Moreover, the providers offer those VMs in different contract models, also called markets. In Amazon, for example, we have two main markets, the on-demand market and the spot market. In the on-demand market, we have VMs with high availability and that cannot be interrupted by the provider. While in the spot market, we have VMs with low availability that can be interrupted by the provider at any time, but those VMs are offered up to 9% discount when we compare it with the on-demand price. So when we start to consider all the decisions the user has to take, as for example, the type of the VM or how many VMs, what market to use, spot or on-demand, and also considering that all the decisions the users made on the cloud impact not only in the execution time of the application but also in the monetary cost of the application, the cloud can become a very complex environment. So in this sense, many works have proposed tools to help in those decisions. One of those tools is called Burst HATE, the Burst Hibernation Aware Dynamic Scheduler. Burst HATE is a modular framework that executes bag-of-task applications subject to a deadline on cloud environments. The framework includes a series of built-in functions such as load balance, native checkpoints, migrations, and recovery procedures, and uses on-demand and spot VMs to minimize the monetary cost and the execution time of the applications. Different from other frameworks that copy just the termination of the spot VMs, Burst HATE also explore the hibernation feature of the spot VMs. So just a short explanations about the hibernation feature. In 2017, Amazon has made some changes in the spot market, and one of those changes was the introduction of the hibernation feature. So instead of terminate a spot VM, the user can decide that the provider hibernated. And when a VM is hibernated, its memory and context are saved by the provider. And if the VMs resume, all the tasks that were running at the moment of the hibernation continue their normal execution. And it's very important that during the hibernation, the time a spot VM is hibernated, the user is not charged by the VM allocation. So as I said before, Burst HATE explored the spot VM market. Specifically, it used the hibernation prone spot VMs, and if that VMs hibernate, burst head can migrate tasks to other VMs, and if the VMs resume, burst head is able to use the VM again. Okay, so burst head was built in a modular way with two main scheduling modules, the primary scheduling module and the dynamic schedule module. And the framework uses a masterwork standard where the masters run locally and send commands through the network to the works that are running in each one of the VMs. So the schedule decisions are taken here locally in the master, while the works are responsible, for example, to monitor the tasks execution and monitor the VMs. Here we see the execution step of burst head. So basically the start scheduling module receive as input the bot application, this file here, and also the set of VMs that can be used, the description of the VMs that can be used to execute the application, and also some input parameters, as for example the deadline of the execution. So the primary scheduling module receives that, the input, and performs an iterative local search heuristic to define initial scheduling map that is generated, and that map contains the VMs that will be launched in the beginning of the execution, and also the initial scheduling strategy that will be followed. Finally, when we have the map, framework start the dynamic scheduling module that deploy the VMs, the workers, and then start the tasks. And after that, when the execution starts, the dynamic scheduling module starts to monitor the execution and reacts to events that can cause deadline violations or increase the monetary costs. So as I said before, in this work, we are interested in the SARS-CoV-2 sequence comparison. So we use the MASOPMP tool, and all the execution will be managed by burst heads framework. So what we did was to get the first sequence from UHAM, the reference sequence, and we compared with all the sequences we could find between December 2019 to November 2020. In the total, we could find 22,600 sequence from in the NCBI database. And our main objective is to show that clouds can be adopted by laboratories that do not have access to a powerful computing platform, and also that the cloud can reduce the monetary cost of the SARS-CoV-2 sequence comparison, even with a very huge number of sequence, and also that the cloud can play a fundamental role in the execution of such applications. Okay, so to execute the sequence comparison with MASOPMP, we first conduct a series of evaluations to define the VMs types that would be better performed to those executions, the task execution strategy, and also what storage service we should use. So first, to define the input set of VMs, we select VMs from the family C, R, and M. Amazon categorized those VMs as optimized for intensive computing, the VMs that are from the family C, optimized for massive and data processing, that is the VMs from the family R, and also general use instances, that is the VMs from the family M. Here we have all the VMs we select. As we can see, we select VMs that has at least 4 vCPUs, and in the total we have 32 VMs that will be used as input to burst heads. In order to have an average execution time of just one comparison in each one of the VMs, we perform execution where we get each one of those VMs and execute just one single comparison. Here we have the result from the family VMs. So here in this graph we have the execution time of just one comparison, the monetary cost in the on-demand market to perform just this comparison, and the monetary cost to perform the same comparison in the spot market. And here we have all the VMs. The VMs are sorted by the number of vCPUs. So here we have the VM with just 4 vCPUs, and in the end we have the VM with 72 vCPUs. In general, if there is an increment in the available computational resource, the execution time of the comparison tends to minimize. But we see, for example, that the VM C5 18XLR that has 72 vCPUs was the slowest to perform the comparison than the VM's C5 9XLR that has 36 vCPUs and is slowest than the VM C5 12XLR that has 48 vCPUs. So that indicates that probably there is not enough parallelism in SARS-CoV-2 comparison for a large amount of vCPUs. So in terms of price, we see a clear difference between both markets, and on average for the C family VMs there is a reduction of 40%, and when we compare the C family VMs with the other VMs, we see that those VMs are able to perform the comparison 21% faster than the VMs from the family M and 32% faster than the VMs from the family R. Here we have the results for the other families of VMs. In terms of price between the spot and the on-demand market, we see the same behavior we have seen in the C family VMs. The very difference in the prices between the spot and the on-demand market to the M family VMs was 39%, and in the case of the R family VMs, the average difference between the spot and the on-demand market was 31%. So it's quite the same behavior we see in the C family VMs, but as we can see, the comparison even in the slowest VMs we have here is a very short task in terms of time. If burst rates worked with those short tasks, it would be necessary to create job with 22,000 tasks, and of course that would jeopardize the execution efficiency of the burst rates. So we modeled the task execution by using the concept of super task. Set of comparison is clustered in just one super task. So when the number of super tasks increase, for example, if I have 10 super tasks, I would have 2,260 comparisons per task. So one task would perform that number of comparisons, and so on. If I have, for example, 100 super tasks, I would have 226 comparisons per task. Here we have the total execution time when we consider different super task size. That make span was computed by considering a deadline of 1 hour, and that is the result given by the primary scheduling map of burst rates. Here we have the cost of that execution, also given by burst rates. Here I have a graph representing the execution time and the monetary cost, consider the different numbers of super tasks. So as we can see in the table and in the figure, the make span the cost tend to decrease as the number of vCPUs increase. We can see here that the number of vCPUs increase, and there is a tendency to decrease the execution time. However, when we have 200 and 300 super tasks, we see that the execution time of the solution increase, but not the monetary cost. We see that with 4 and 500 super tasks, what increase in fact is the monetary cost, and that happened because if we look in the table, that solutions reach the vCPU limit. So in the Amazon account we performed our tests, we have a limit of 300 vCPUs in the on-demand market and 300 vCPUs in the spot market. So in this case here, since burst rates reached the vCPU limit, the internet local search heuristic was no longer able to find a well-balanced solution between the make span and monetary costs. So compare the case when we have 10 super tasks with the case when we have 100 super tasks. We see that with 10 super tasks, the make span was 63% greater than the case where we have 100 super tasks. The monetary cost of the execution with 100 super tasks reduced in more than 27% compared to the execution with 10 super tasks. And that happens because when we have few super tasks, as for example 10 super tasks, the internet local search heuristic is not able to launch more than 10 VMs since it cannot distribute the tasks between the VMs. But there is another characteristic when we are considering the spot market. There is the fact that the spot VMs can be revocated, in this case hibernated. Because of that, we know that if we have execution with lots of spot VMs, we also increase the chance of hibernation. So for our practical evaluation that I will show next, we selected the solution with less than 30 VMs and with the make span more than 1000 seconds. So because of that criteria, we select the solution with 60 super tasks. So the next step is to define the storage service that we use in our evaluation. In the cloud environments, we have different storage options that can be hired and used with the VMs. In AWS, for example, we have different storage services, for example, S3, EBS, EFS, among others. and those storage services have different features, purpose, and prices. In this work, we evaluate the S3 service and EBS in the context of the Maso PMP, and we use those storage services to keep the input files and also the output files. And we want to know how those services would affect the execution time. So we select S3, that is a distributed storage service, and EBS, that is a local storage service. S3 is probably the most popular storage service of Amazon. It can be utilized to store and recover any amount of data, and the objects that can be stored in S3 can have 0 bytes up to 5 terabytes. The other storage service, Amazon Elastic Block Store. The EBS offer local storage volumes with capacity that goes from 1 gigabyte to 16 terabytes. The volumes are persistent and can keep without any VMs associated. So to evaluate the impact of the execution, we consider a supertask with only 4 sequences, and we use the VM C590X and the difference between the execution time when we use each one of the services was huge. In EBS, the execution took only 14 seconds. In S3, the time was 2,188 seconds. And that happens because Amazon does not offer native support for use S3 as a file system in the VMs. Thus, we use a tool called S3FS Fuse, provides an interface to S3 and mount it as a POSIX file system. But the S3FS Fuse provides a very poor performance when we have a lot of I/O operations randomly reading and writing, and that is the case of Maso PMP. In this case, we see that the S3 become prohibitive to use in our tests, so we select EBS volumes. Okay, so to the practical evaluation, as I said before, we select this case when we have the solution with 60 supertasks that has 376 comparisons per supertask, and we fix the deadline in 1 hour using 24 spotting instance, give us a make span of 21 minutes, and we compare our execution of burst rates in a case where we don't have any spot revocation, any hibernation, with the case where we use just on-demand VM. So it's the same solution give by the primary scheduling of burst rates. In this case, we have basically the same make span for both cases, or both solutions, but the monetary cost reduction was for more than 15%. But as we know, we have scenarios that has hibernations and resume events. And since cloud users have no control of the events of hibernation and resumes, we use Poisson distribution models to emulate different partners of hibernation and resumes. So in this case, we have distinct Poisson distribution functions, one to emulate the hibernation and other to emulate the resume. And to compute the value of that function, we define a hibernation rate and a resume rate. For example, here in the first scenario, we have a hibernation rate of 5, while the resume rate is 0. That means that we can have hibernation during the execution of that scenario, but we don't have resume events because the rate is 0. And those are the results. Here in the table we have each one of the scenarios, the number of hibernations that happen during the execution. This is a variation of 5 executions, and the number of resume happened during the execution, and the number of additional on-demand VMs that was launched by burst heads because of the hibernations. Then in the sequence we have the monetary cost of the executions, the average monetary cost, the average make span, and here in the two last columns of the table we have the difference between the monetary cost and the make span. Consider the solution that uses only on-demand VMs. The first thing we can see is consider that the deadline was 1 hour. Burst heads was able to meet the deadline in all the scenarios, in all the cases, and also was able to reduce the cost for other cases. But for example, here in the first case, where we have the worst case scenario because we have biggest rate of hibernations but there is no resume in this case, burst has had to launch more on-demand VMs, so the monetary cost was just 2% less than the on-demand strategy. And also we see that the difference in the make span is quite huge because of all the overheads to launch new VMs and move the tasks to those VMs in the case of the hibernations. Okay, so in scenario 2 we can see how the resume events impacting the final monetary cost of the execution, because even in scenario 2 we have more hibernations, the number of hibernations was bigger than in scenario 1. Because we have the event of resumes, the difference in the monetary cost was almost 30% when we compare it with the on-demand solution. And finally, in scenario 3, we have the case where the hibernation and the resume has the same height, 5. And in this case, the framework was able to reduce the monetary cost in 32%. So, our evaluation showed that with Mas OpenMP run on top of burst heights, we could align more than 22,000 SARS-CoV-2 sequence. We compare our solution with on-demand strategy, and in this case, burst haze was able to reduce the monetary cost by more than 15% in scenarios with no spot hibernations, and also burst haze was able to reduce the monetary cost and meet the deadline even in the case where we have lots of hibernations. Therefore, our evaluation showed the benefits in terms of monetary cost reduction of use burst haze, but also that the cloud can play a fundamental role in the problem of comparisons of SARS-CoV-2 sequence. Okay, so thank you very much.